Chapter 3 has essentially two different kinds of long answer problems associated with it. One kind is purely to do with vectors and vector addition, breaking vectors into components, and the second kind is projectile motion problems. So what I'm going to do is I'm going to work through one example of each type of problem for you today. So the first problem says, a car travels 21 kilometers to the northeast, then 15 kilometers to the east, and finally 28 kilometers to the north. Express the position vector from where the car started to where it finishes in terms of components. What is the car's total displacement? So what we need to do is we've got three different vectors for the car's motion, and we need to add those together to get our final position vector and then find its length in order to get the total displacement. So when you do a vector problem, always start off by drawing a picture. So now we've got something that's moving north and east. So let's draw the points of a compass. So north, east, south, and west. And I didn't make south and west very long because we don't have any motion in those directions. Okay, so let's draw our vectors on. So first of all, the car travels 21 kilometers to the northeast. When it says northeast, that means exactly halfway between north and east. So that means it's going to go up the diagonal here. And let me estimate that and say that's 21 kilometers. Okay, after it's done that, it travels 15 kilometers to the east. So directly horizontal on this picture. And I'll make my vector a little shorter than the first one because it's only 15 kilometers long. And then finally it goes 28 kilometers north. So I need to make a vector that's longer than my first vector going north. So what is it asking me to do? It's asking me to express the position vector from where it started to where it finishes. So that means from the origin up to this point here. So I need to find this red vector in terms of components. So it's going to be partly east and partly north. So how am I going to do this? Well, the easiest way to do it is to break each of my original three vectors up into components. Okay, so let's start off with vector 1. I traveled 21 kilometers to the northeast. And let me draw this for you. So here I've got 45-degree angle, and the length is 21. I want to find the x component and the y component, which in this case is the east component and the north component. So start off with the east component. The east component is this side of the triangle. This side of the triangle is touching the angle, adjacent to the angle, so I'm going to use cosine. Alright, so if we call this vector vector A, then the east component of vector A is going to be the length of A times the cosine of 45 degrees. And if I plug that in my calculator, make sure my calculator's in degrees, I get 14.85 kilometers. Okay, and of course, if you look back at the problem, you see everything's in two significant figures, but I'm not going to round everything off now because I got to wait till I'm at the end of the problem before I round off. How about the north component? The north component is this side of the triangle. This side is opposite to the angle, so I'm going to use sine. 21 sine of 45 degrees. And sine of 45 and cosine of 45, you should know, are the same. So those two components are the same. So I got 14.85 east and 14.85 north. So that's vector A. Vector B, we're going to call this one that's going horizontally. Vector B, well, I don't really need to draw. Let me do that in black ink. I don't really need to draw vector B. It's all horizontal, so the east component is the 15 kilometers, and the north component is 0 kilometers. It does not go north at all. Okay, how about the last vector? We'll call it vector C. Vector C doesn't have any east component. It's going straight up, straight northwards on that diagram. And the north component is 28 kilometers. Okay. Okay, so I've got everything broken into components. Now I can find my final answer. The displacement vector, let's call it vector D. Vector D is going to be the total east component. So the east component of all three of the vectors together to the east plus the total north component. So add up the north component for those three vectors to the north. Okay, so I've got 14.85 plus 15 plus 0 to the east. And if we draw that in terms of our standard unit vectors, we have I hat going horizontally and j hat going vertically. I could write that as I hat. And to the north, or j hat, I've got 14.85 kilometers from vector A, 0 from vector B, and 28 from vector C. Write that as j hat. So that is 29.85 to the east plus 42.85 to the north. And this is looking close to our final answer for the first part. So now we should round it off to two significant figures. You see each of these vector lengths is two significant figures. So I would say my displacement vector is 30 kilometers to the east plus 43 kilometers north. And remember, when you give a final answer on the test, always put your units in. Always round off to the right number sig figs, and always put your units in if you don't want to get half a point taken off or something. All right, last part. What's the total displacement? Well, the total displacement is just the length of vector D. Okay, so total displacement is equal to the magnitude of that vector. And the magnitude of that vector, remember Pythagoras, you add the east, and you add east squared plus north squared. So it's going to be, and again I'm going to use most number significant figures, 29.85 squared plus 42.85 squared by Pythagoras. Take the square root, and I get 52.22 kilometers for the displacement. And I'm going to round that to two significant figures, so that's going to round down to 52 kilometers. Another thing you might be asked is, what is the angle at which the car moves? Well, the angle, now if I draw my displacement vector, my displacement vector is about 30 to the east. Let me draw that in red. 30 to the east and 43 to the north. So if I want to solve for this angle here, so I've got 42.85 and 29.85. The tan of that angle is opposite over adjacent. So tan theta is 42.85 over 29.85, which is about 1.44. And so to get my angle is going to be the inverse tan of that. And I get 55.1 degrees. And you would probably express that as 55 degrees north of east. And again, it's always important to draw the picture, because if I had drawn my vector going south, I would still have got my angle to be 55 degrees, but I would have had to say 55 degrees south of east. So always draw your final vector so you know whether the components are positive and negative and which axis the angle is with respect to. Okay, the second kind of problem is a projectile motion problem, and I've put in this projectile motion problem pretty much everything that you could be asked to solve for. So here we have a projectile is shot at an angle of 34 degrees to the horizontal with an initial speed of 225 meters per second, and it lands at the same height as which it takes off. And what we want to know is, what's the maximum height that the projectile reaches? What is its velocity when it gets to its maximum height? How far does it travel horizontally before it hits the ground? In other words, what's the range? And how long is it in the air? What's the time? All right, so start off, always draw a picture. So draw a picture of what we have. We've got motion in both the x and y direction. And my projectile takes off and lands at the same height. All right, so what are the things that we're asked to find? We're asked to find the maximum height. So that's going to be here. We're asked to find how far does it travel. We're asked to find how long is it in the air. And we're asked what's its speed when it gets to the top part, when it gets right to this point here. All right, so what do we know about projectile motion? Well, we know that a projectile travels with the same speed always in the x direction. Okay, so Vx is equal to V0x because we're ignoring any air resistance. And so that means there's no acceleration in the x direction. And so the position is always just the speed times the time. Okay, so if I know at what time it hits the ground, let's call that T2. If I know what time it hits the ground, then I know the distance that it travels is its initial speed times T2. All right, so to find the answer for part C, I need to know how long it's in the air. So I actually need to know my answer for part D before I can solve part C. Okay, what else do we know? Well, we know that if we study the motion in the y direction, it's just like what we did in chapter 2 with free fall. We've got the speed in the y direction varies like this. The position in the y direction follows the standard equation, where the acceleration in this case is negative g. And of course we have our Vy squared equals V0y squared minus 2g times y minus y initial. So we have our standard 3 equations and only one equation for the horizontal. Okay, so what is it that we know and we don't know? Well, they tell us that it's shot at 34 degrees to the horizontal, an initial speed of 225 meters per second. That's all we're given. So let's draw that on here. So I've got my initial V is 225 meters per second at an angle of 34 degrees. Okay, so from that I can get my x and y initial speed. So my V0x is this side of the triangle. This side is touching the angle. So that's going to be cosine. Adjacent is cosine. So V0x is equal to V0 cosine of 34. So that's 225 cos 34, which gives me, check my numbers, 186.53 meters per second. Okay, so we can get that directly from what we're given in the problem. And for y, well, if x was cosine, y is going to be sine. And we can look at our triangle and say, okay, y is this side, which is opposite to the angle, so that's got to be sine. So 225 sine of 34 is equal to 125.82 meters per second. Okay, so I've already got my V0x, and I can plug that directly in here. As soon as I get a time, I can get my answer for C. Okay. What is the maximum height that the projectile reaches? What's its speed when it reaches the maximum height? Well, to do that, we need to understand about projectile motion. So what happens in projectile motion? What happens in the y direction? The thing starts off with its maximum speed. It goes up, slows down, stops, and comes back down again. So if I just look at v0y, when it's right at the top here, vy is equal to 0. What's Vx? Well, Vx is always the same because we said there's no friction in the x direction. So when the object is at its highest point, it's got no speed in the y direction. Its speed in the x direction is equal to its initial speed, which we already know. Okay, so my total speed is just equal to the horizontal speed. So I've already got my answer for B. So for B, let me write this in black so it comes out a little bit better. So for B, V at the top is just equal to Vx, which is just equal to V0x. So it's 186.53 kilometers. Okay, and I got to round this off to sig figs now because it's the final answer for this part. Here I've got 2, here I've got 3. We always round it to the least number of significant figures, so that's got to be rounded off to 2. So it's 190. I don't know where I got kilometers from, sorry, that should be meters per second. 190 meters per second. Okay, so you see how easy it is to mess up. Make sure I was putting down units, probably a holdover from the previous problem where I was doing kilometers. Make sure your units always look right. Okay, so the speed at the top is 190 meters per second, and that's the answer to part B. And you can see that when you do problems, you don't always get the answer to the first part of the problem first. And when you do the problems on a test, do them in any order. Just make sure that they're neat enough and draw a circle around each answer and make sure I know that that's the answer for part B. Alright, what's the maximum height that the projectile reaches? Well, whenever you do a problem where it asks you for maximum height, the key is to use the fact that when it gets to its maximum height, the speed in the y direction is 0. Okay, so at maximum height, Vy is equal to 0. Okay, so Vy is equal to 0. I know my Vy0 was 125.82 meters per second. Okay, what else do I know? I don't know my position. That's what I want to find. So I want to find, that's called y max. I know my y initial was 0. Okay, I don't know my time. And I know my acceleration is negative g, and that's worked right into the problems already. So let's go back up and look at the equations to see what we can use. Okay, I know my Vy, I know V0y, I know g, so I can find t. Alright, that's not going to help me find y max, but it's sure going to help me find the time that I need for part D. Alright, so let's keep that in mind. We can't use it for part A, but we could use it for part D. Alright. What next? This one? Well, this one's got t in it, and since I don't know t, I can't find y. So that means we're going to have to use the last equation. Okay, so Vy squared is equal to Vy0 squared minus 2g times y, which is y max, minus y initial, which is 0. Okay, so let me simplify that down. So Vy squared is Vy initial squared minus 2g times y max. I need to rearrange that to solve for y max. So let's see. Oops, I need to put a 0 on there. Let's take Vy0 over onto the other side. And then to solve for y max, I just need to divide through by negative 2g. Okay, so y max is equal to Vy squared minus Vy0 squared over negative 2g. And you should see now that this problem is very similar to a problem that we did back for chapter 2 with free fall. And we're doing just a rearrangement of the same kind of problem to get the same kind of answer. Alright, so now just plug in my numbers. Y max is equal to Vy squared. Well, the speed when it's at the top in the y direction is 0. Initial, 125.82. And I'm going to square that. So I'm going to get a negative number on top minus 2 times 9.8 meters per second squared on the bottom. Negative over negative is going to give me a positive. So again, make sure you put your numbers in the right way. Vy is 0, Vy initial is 125.82. Alright, so put that together. I get 807.7 meters is my range. And rounding to two significant figures, that's 810 meters. Okay, so there's my answer for part A. So I've got A and B. C we said we can't do till we got the time. And so now let's do D. Okay, so we said that we could use this equation here to get the time when it reaches the peak. How do I get my total time? Well, if an object goes up and lands at the same height that it took off at, then it's going to take the same amount of time to go up and the same amount of time to go down. So if I can find this time here, all I have to do is multiply it by 2 and I can get my total time. Okay, so we're doing part D. T2 is going to be twice the time to the maximum height. Okay, we said that we could use this equation here. So at y max, I've got Vy is equal to V0y minus GT. And so T is equal to Vy minus V0y over negative G. So it's 0 minus 125.82 meters per second divided by negative 9.8. Again, I got negative over negative. And my time is equal to 12.84 seconds. Okay, so that means that T2 is equal to twice that, which is equal to 25.68 seconds. And rounding, that's 26 seconds. Okay, so that's my answer for part D. Or what do you do if you've got something that doesn't land at the same height? Well, in that case, what you would do is you would use the final equation, and when you solve it, you're going to have to use the quadratic formula. Okay, so let's do that as well. So if I use that equation, I need to say, okay, so at this position here, y2 is equal to 0, y initial is equal to 0, v initial y is that, and I know my g. Okay, so I can say, or I use 0 is equal to 0 plus 125.82 times T2 minus 1/2 times G, 9.8, times T2 squared. Okay, so that gives me that 0 is equal to 125.82 times T2 minus 4.9 times T2 squared. Okay, so this is just a quadratic equation, and if you had the thing landing at a different height to where it took off, then you'd have another number in here that would be a constant equal to the height difference. Okay, so we need to solve this using the quadratic formula. Alright, so my quadratic equation is AT squared plus BT plus C is equal to 0. With the solution, we did this already for the last chapter, negative b plus or minus the square root of b squared minus 4ac over 2a. And that's our solution for time. So what's b? In this case, b is equal to 125.82, a is equal to negative 4.9, and c, I don't have a c term, so c is equal to 0. All right, and if I plug that in for time, I get 2 times. I get t is equal to 0, which is my solution for the positive, and for the negative, I get t is equal to 25.68 or 26 seconds. So I get exactly the same answer that I did before. What does the t equals 0 solution mean? Well, the t equals 0 solution is, remember, we're solving for times at which the position is 0. So I've got one place over here where it's at a height of 0, and another place over here where it's at a height of 0. So this first solution just tells us, well, when you start off, you're at a height of 0. So that's not the answer I want. I want 26 seconds. All right, so I've got my answers to A, to B, and to D. Finally, we want to find our answer for C. And we said for C, we were just going to use this, that the range is equal to the initial speed in the x direction, which is always the same speed in the x direction, times the time. So that's 186.53 meters per second times t2. And again, I'm not going to round these numbers. You round it at the end. So 25.68 seconds. I get 4,789.63 meters for my range. Round to two significant figures. That's 4,800 meters. So that's about 5 kilometers. Okay, and if you can do this problem, I promise you will be able to do any projectile motion problem. These are the kind of things that we ask you. How high does it go? How far does it go? How long is it in the air? And what's its speed at various points? So remember, the speed in the y direction starts at its maximum, goes to 0 when it's at its peak, and then starts to increase in a negative direction. The speed in the x direction is always the same. Trick question, what's the acceleration? The acceleration at any point is the same. It's always equal to minus g.